Today we're going to be talking about improper integrals. Now, improper integrals have several different forms. The most common one, though, is taking an integral from some constant to infinity or from negative infinity to a constant. So how we're going to do an improper integral from some constant to infinity is we're going to use limits. So this is going to be the limit as b goes to infinity of the integral from a to b of the function. Similarly, with negative infinity to b, this is going to be the limit as a goes to negative infinity of the integral from a to b of f of x dx. For infinity, negative infinity to infinity, we're going to break it up into negative infinity to b, and then from a to infinity, and then we'd apply the limit rules after that. Okay, so let's do an example. We have the integral from 1 to infinity of 1 over x squared. Now this might have a value. It may also be infinite. If that's the case, we call it a divergent integral. So this is going to be the limit as b goes to infinity of the integral from 1 to b of 1 over x squared dx. So we'll evaluate this integral, and the limit's going to go along for the ride for a little bit here. So the integral of 1 over x squared is negative 1 over x. We're going to evaluate that from 1 to b. So this is going to be the limit as b goes to infinity of negative 1 over b minus a negative, so this will be plus 1 over 1. Well, as we go to infinity, 1 over infinity is going to go to 0. So what we're left with is the limit as b goes to infinity. This is going to go to 0. This is going to go to 1. So this integral is 1. So in this case, we got a value. Here, we've got the integral from 1 to infinity of 1 over x. So this will be the limit as b goes to infinity of 1 over x, of the integral from 1 to b of 1 over x dx. So the integral of 1 over x is natural log of x. So we're going to evaluate this from 1 to b. So we're going to have the natural log of b minus the natural log of 1. As b goes to infinity, the natural log of that is just going to keep going bigger and bigger and bigger. So this is going to go to infinity. This is 0, but that doesn't really matter because this is infinite, which means this one is divergent. Okay, so here I've got the integral from 1 to infinity of 1 over x to the 1.01. So we have the limit as b goes to infinity of the integral from 1 to infinity of 1 over x to the 1.01 dx. Well, this is kind of a funny power, so I'm going to rewrite it just so it's a little bit clearer what we're doing. So this is going to be the limit as b goes to infinity of the integral of 1 to infinity of x to the negative 1.01. Because dealing with powers makes our life a little bit easier. So this integral is just going to be the power rule. So I'm going to add 1 to this. leave a space here. So if I add 1, I have negative 0.01, and then I'm going to divide by that. We're going to evaluate this from, sorry, I forgot to make this b, 1 to b. Okay. Okay. Well, 1 over 0.01 is really negative 100, and then I'm going to rewrite this back in the denominator. Okay, so negative 1 over 0.01 is 100, and then we have this in the denominator. This is not there anymore. So this is going to be the limit as b goes to infinity of negative 100 over b to the 0.01 minus negative 100 over 1 to the 0.01. This denominator, even though this is a really small power, this power is positive. So it will increase exponentially, slowly, more slow than if it was like a b squared, but it still is going to go to infinity. So that you're going to have negative 1 over infinity, which is again 0. So then we're just left with minus negative 100 over 1, so this integral is 100. Our next integral goes from negative infinity to 0. So this is going to be the limit as a goes to negative infinity of the integral from a to 0. Okay, well, integral of e to the x is e to the x. So this is going to be e to the 0 minus e to the a. Well, e to the a, as we go to negative infinity, is going to be 0. If we have a e to the x graph, it's going to look like this. So as we go to negative infinity, it goes to 0. So we have e to the 0 minus 0. E to the 0 is 1. So our integral is 1. All right. So this one we're going from negative infinity to infinity. So it may converge, it might diverge. First thing we're going to do is split it up into two integrals from negative infinity to 0. And from 0 to infinity. Then we'll apply our limits. So this one's going to be the limit as a goes to negative infinity of the integral from a to 0. This one's going to be the limit as b goes to infinity of 0 to b. Okay, and then we'll take these integrals. So the integral of 1 over x squared plus 4 is our tangent inverse rule. So this is going to be 1/2 tangent inverse of x over 2, evaluated from a to 0. And this integral is the same thing. So we're going to have the limit as a goes to negative infinity, 1/2 the tangent inverse of 0 minus 1/2 tangent inverse of a over 2. plus the limit as b goes to infinity of 1/2 tangent inverse of b over 2 minus 1/2 tangent inverse of 0. All right, so let's talk about tangent inverse for a second. If we graph tangent inverse, actually let me graph tangent first and then we'll graph tangent inverse. So tangent, remember, is undefined at pi over 2 and negative pi over 2 because it's sine over cosine and cosine is undefined there. So the graph of tangent is asymptotic. It approaches those two values. Inverse tangent then looks like this. So as we go to infinity, it does approach a specific value, pi over 2 at infinity and negative pi over 2 at negative infinity. So as we go to infinity, negative infinity, this is going to be 0. This, as we go to negative infinity, is going to be negative pi over 2. Here, as we go to infinity, this is going to be 1/2 times positive pi over 2 minus 0. So we get a 0 minus a negative 1/2, so that's going to be a positive pi over 4. This will be positive pi over 4. So we get pi over 2. For example 5 here, A, B, C, and D, the derivations of it, you can look in the PDF version of the notes. But I kind of want to just bottom line it for you right now, because right now these integrals are probably a little bit hard to wrap your head around. So I'm going to make the conclusion of all of this. And like I said, you can look at the derivation. Okay. The conclusion, if we have an integral from 1 to infinity of 1 over x to the p. Okay, and we've done several of these. So I'm going to look at the ones that we've already done. The first 3 were all examples of this. So this one, x squared, we got a value. This one, 1 over x, it was divergent. This one, 1 over x, 1.01, we got a value. So when it was 1, it diverged, but as soon as it got a little bit bigger, 1.01, 2, and so on, we got a value. So the conclusion here is it converges or has a value when p is greater than 1. So if it's 2, if it's 1.001, it's going to have a value. It diverges if p is equal to 1 or a number less than 1. The switch of that is true when we go from 0 to 1. So if 0 is asymptotic, this one converges if this number is less than 1. So this is, like I said, the opposite of that. It diverges when p is greater than or equal to 1. So in both cases, if it equals 1, it's going to diverge and diverge. But the switch is, they're flipped. So these are some rules that you'll want to know. We will do a lot more with convergent and divergent series second semester. But for right now, for the improper integrals, if it's in this format, these are the conclusions. Okay, the next couple of examples are not to infinity, but they're still improper integrals. This one's improper because at 1, this function is undefined, but there may still be a value. So what we're going to do is use limits again, but now we're going to let a go to 1 and replace the 1 with a. Okay, so this integral, this is 1 over essentially x, so that would be natural log, but because there's a negative here, we have to take that into account. So this is going to be negative natural log 1 minus x. And if you want to do a u substitution within these, that's fine. So this is going to be the limit as a goes to 1 of negative natural log 1 minus 2 minus the negative, so I'm going to make that a plus, natural log of 1 minus a. Here, we're looking at the natural log of 0, and natural log looks like that. So as we go to 0, this is going to negative infinity, which means this is divergent. Okay, this next one is again improper because it contains between 0 and 2 asymptote. So we need to split this up into the integral from 0 to 1. And the integral from 1 to 2. So now we'll use our limits to replace the 1 here and the 1 here. So the top one we'll replace with b. The bottom limit we replace with a. And you can pick a different letter if you want, but the commonly used ones are a and b. So this would be a. So I'm going to rewrite this to make my life a little easier again. I'm going to rewrite this using the negative exponents. This will be the integral from 0 to b of x minus 1 to the 3. To the negative 3. So when we integrate it, we're going to add 1 to the power and then divide by that new power. So it's going to be a negative 1/2 x minus 1 to the negative 2, evaluated from 0 to b. Same thing here. And we're going to make all these replacements in our definite integral. And we'd keep going, but I'm going to stop here because what this is going to happen is even though this is in the denominator, it's still going to have an asymptote here. So this is still going to go to infinity. So sort of unsatisfyingly, this again is divergent. And we could keep going on but you're going to get the same conclusion anyway. All right, next one, another infinity. So this is going to be the limit as b goes to infinity of the integral from 0 to b x squared e to the negative x. Okay, so this one we're going to use integration by parts because we have a product. I'm going to use my rapid repeated because it makes life a little bit easier. Log poets means our polynomial is what's going to be our u. Take those derivatives. Integrate e to the negative x, which is just going to alternate between positive and negative e to the negative x. Okay, then we have our diagonals. Plus, minus, plus, minus. So this is going to be the limit as b goes to infinity. This integral is now going to be negative e to the negative x times x squared. Squeeze x squared in there. Our next one is going to be minus 2x e to the negative x. Our next one's going to be negative 2e to the negative x minus the integral of 0. Okay, and we're going from 0 to infinity. Sorry, b. So we're going to replace all the x's with b. So we're going to have negative b squared e to the negative b minus 2b e to the negative b minus 2e to the negative b minus 0. So if we plug a 0 in here, that's going to go away. That's going to go away. Here, we're going to have minus, so 0 minus 2e to the 0. As we go to infinity, e to the negative x is going to go to 0. So this goes to 0, this goes to 0, this goes to 0. So what we're left with is this. So we're going to have minus negative 2e to the 0. So that's going to end up being a positive 2. So this one says if the integral from 2 to x of f of t is 10x over the square root of 2x squared plus 1 plus 7, then what is the value of this? So this is going to be the limit as b goes to infinity of the integral from 2 to b of f of t. This is going to be the limit as b goes to infinity if this integral now gets replaced with all of this. I guess the integral from 2 to x is this, then the integral from 2 to b. These are going to be b's. But what we're looking at here is what's this limit as we go to infinity? Well, that's going to depend on the degree. Well, this is a degree 1. The square root of a squared is degree 1. So this is going to be 10 over the square root of 2, because it's the leading coefficients, plus 7. So those are improper integrals. Knowing those rules is helpful, and then just applying the limits to help you deal with those infinities and asymptotes.